to use virtual camera. Oh, we're going live. Okay.
Okay.
Hello, everybody. And this is the third talk today in the Pink Track. And a short note from to our listeners from our sponsors. The most active participants in the Q&A section are going to win an ebook from our sponsors, Pact. So use that Q&A function, ask our speaker questions, preferably about the talk that she's going to give. But without further ado, I want to introduce you to Nicole van der Hoeven, who will tell us about observability for chaotic load testing. And her talk is called Schrödinger's Pokémon. So, Nicole, the floor is yours.
All right. Thank you. Goedemorgen iedereen. That's good morning, everyone. I am Nicole van der Hoeven. I'm a developer advocate at K6.io, which basically means that I try out cool things to do with K6 and then I tell people about it. I've been in performance testing for over 10 years now, and this is Schrödinger's Pokémon, observability for chaotic load testing. So today I'm going to combine three things that I love, which is Pokémon, load testing, and observability. I'm specifically going to use K6 as the load testing tool and Prometheus and Grafana for metrics and visualization. I do happen to think that this is a killer combination, although I'm biased for reasons I'll get into later. But the principles that I discuss about load testing and chaos engineering will be applicable to any project and any tools that you want to be using. So here's what you're going to learn in the next 40 or so minutes. And by the way, the slides are going to be made available. I'll give you the link at the end, so there's no need to take screenshots. First, what is chaos engineering? We'll talk about what it means, the process it involves, and how it relates to testing. Second, I'll go through the steps of chaos engineering using I'll talk you through the tools that I used, the script that I wrote, the tests I ran, and results. And third, I'll wrap up by talking a bit about why observability is critical for chaotic load testing. Let me know as well if you can't see the slides completely or anything. I'm trying something new, so let's see how it goes. Here's the definition of chaos engineering by principlesofchaos.org. Chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capacity to withstand turbulent conditions in production. So the emphasis here is mine. Notice that this definition doesn't talk about preventing turbulent conditions or failures. It talks about finding out how the system will respond to them. It's a pretty big difference from testing. There are 4 steps to engineering chaos. In the first step, we will define and prepare a steady state. Think of this like the control group. Before we start running tests and trying to break things on purpose, we need to have a good understanding of what normal looks like for our application. That way, we'll have a baseline to compare our test results to. The second step is hypothesis. A hypothesis is a statement of what you're testing. So this is a good opportunity to come up with very specific assumptions that we've made about our application. It's not enough to say that we want the application to respond quickly, because we need to identify concrete metrics that we can measure quantitatively. And in the third step, we execute experiments that try to disprove our hypothesis. Now, that part's important. We're not trying to confirm what we already think. We are going out of our way to try to prove ourselves wrong. And finally, in the fourth step, we analyze the results. We compare the results to our experiments with our hypotheses and think about what we could do to improve the application. Now, does this process sound familiar to you? In a lot of ways, I think it sounds like testing, doesn't it? In testing, we start by establishing a baseline. So how does the application work now? And then we discuss with stakeholders how we want it to work in the future. And we formalize our objectives into requirements. We write tests that will check whether those requirements are met. and we execute them to verify how the application behaves. And finally, we analyze the results. So I think that sounds pretty similar, right, between chaos engineering and testing. Now, here's what I think, and maybe it's a controversial opinion. I consider chaos engineering as a testing discipline. They are similar in intention. The goal of both a chaos experiment and a test is to improve software quality through repeated and methodical verification. And as I showed in the previous slide, their processes are pretty similar. They share some similar concerns, like how close an environment is to production, or the reliance on test data, and the importance of those initial requirements. And of note for testers like us, I think there's a lot of overlap in the skill set required between chaos engineering and testing. There's still some key differences, however. And one difference is a difference in attitude. In testing, we seek to prevent failures. Chaos engineering's primary focus is to handle failures gracefully. So it's going to take as a given that an application will fail in production. And it starts from that assumption. So testing does tend to focus on things that are likely to happen, like the most popular page being accessed during a typical user flow during peak load. But chaos engineering encourages us to ask, what if? So what if the main server goes down? What if another page gets all the traffic and we didn't expect that? What if one of the services experiences an outage? It's a slight shift in perspective, but I think the two are still compatible. And another difference is in the tools that they require. So chaos engineering is still relatively new compared to software testing in general. So they tend to require different tools. I'm not aware of many fully featured testing tools that can also do chaos experiments, and the reverse is true too. I'm not aware of any chaos tools or chaos engineering tools that are also capable of carrying out fully functional test suites. So this is a big obstacle to testers. What am I saying? To testers fully adopting chaos testing. In the next few slides, I'll show you how I managed to get over this obstacle, because it was a bit of a hurdle for me as well. So here's the application I want to test, or at least a publicly available version of it that I started from. It's called PokeAPI, which is why I'm wearing these awesome ears. And it's essentially a big database of different Pokemons throughout various games. They have an API that you can use to query the database for Pokemons, moves, items, abilities, and many more things. So here's the problem. Imagine that Pikachu here is my application. What happens when I put it into a box? Well, then I don't see how it's doing, right? The box is preventing me from being able to see exactly what's happening. Since I've just put it into a box, I can kind of assume that for right now, it's fine. But this is as much as I'd know about the app if I just deployed it as is, which isn't great. What if things happen to the box in the meantime? In production, many things happen that I may or may not expect. So how would Pikachu respond to high load? How does it respond to chaos, maybe in the form of Team Rocket? Erwin Schrödinger, this is the title of the presentation. Erwin Schrödinger is an Austrian physicist who conducted a similar thought experiment, although he didn't use Pokemon, to prove a different point about quantum superposition, things that I don't know anything about, but I'm liberally repurposing what he thought in his experiment to describe the situation that Pikachu is in. At this point, while Pikachu's in the box, I don't know whether it's alive or dead. And that's something that I'll have to address in my chaos testing because I need to know how Pikachu's doing. The first step in chaos testing, and at this point I'm the term chaos testing interchangeably with chaos engineering, is defining the steady state. What is normal for the application? How does it behave before throwing chaos and load into the mix? So here's the structure of my app. I took the source code for Poke API, which is available on GitHub, and I created manifests for it. So there's a link here in the slide to my fork of the repo that includes those manifest files. And then I put the application on a Kubernetes cluster, which is managed by DigitalOcean. I set it up so that it consists of 3 physical nodes. It consists of 2 web pods, 3 app pods, a pod for the database, and 1 for the cache. I also added replicas to improve availability and performance. To address the issue of me not being able to see into the box, I also installed Prometheus and Grafana on the cluster. So Prometheus is a time series database and is also a great tool for capturing metrics. It works out of the box, and I like out of the box because it means less setup for me. Grafana is a visualization tool that will let me see the metrics from Prometheus and also from K6. And I chose Grafana because, like Prometheus, it's part of the Grafana Labs stack of projects, so they work well together. Just a disclaimer here, though, I would be remiss in not mentioning that K6, whom I work for, was acquired by Grafana Labs a few months ago. So my tool choice is clearly biased here, but for what it's worth, I've done this presentation, but I did it with New Relic, so I don't think it really matters which observability platform you're using. I think you can substitute whatever you're already using in here, although it's difficult to look past Prometheus because it's a CNCF project for a reason, and that reason is that it's good. So this is what I had to do to install Grafana and Prometheus. Here is the series of commands that I ran to install them onto my cluster via Helm. Helm's a package manager for Kubernetes. So it was a matter of adding the Helm charts for them both and then running the command to install them. Now, Prometheus does have a UI, but I didn't really think it was necessary in my case since I just wanted everything in one place, and that would be Grafana. So after that, I forwarded the port that Grafana is running on, and then I got the password to log into the UI. So this way, I'm running Grafana inside my cluster in the DigitalOcean cloud, but I can still access the Grafana UI locally. And then I had to make sure that Prometheus and Grafana could talk to each other. Luckily, they're built to work together well. So after I added Prometheus as a data source, I also found out that there was already a Grafana dashboard specifically for monitoring Kubernetes clusters using Prometheus. That meant that after installing Prometheus, I could just immediately see information coming in about my cluster. So I didn't create any of these panels. This is what the ready-made dashboard looked like in Grafana, which was awesome. So this is what my setup looks like. I have my Pokémon in a box, but Prometheus and Grafana are installed inside the box. Prometheus is gathering information about Pikachu. I imagine it's checking for, vital signals, respiration rate, and then Grafana is then able to see those metrics and make them available for me to access outside the box. This approach works really well because now I know exactly what's happening inside the box and I can get immediate feedback about how the application is responding to my experiments. Installing Grafana and Prometheus were essential for me to establish the steady state. It goes back to the idea of a control group to compare the experimental group or the out of control group to. In a real, or meaning production-ready application, you might not need to do much more than observe and monitor via Grafana as users access the application. Since in this case, I'm the only one using this application, I wanted to run a small test of 10 users to serve as the baseline, just enough to introduce some sort of load. And to do that, I used K6. K6 is a load testing tool that is designed to be performant. It's written in Go, and that's why it's so performant, because it has some innate advantages there. But the scripting is done in JavaScript. So this is an example of a basic K6 script. And what I'm doing here is in this function catch 'em all, I'm querying my app for information about Pikachu. So it checks to make sure that the response, the body contains the word Pikachu and not like error or something, and that the response returned was an HTTP 200. It's important to do both because depending on how the application is set up, it is possible to get an HTTP 200 back, but the response is error. So then I also included a think time here, that's the sleep, to simulate a real user reading that information. Just because hammering an application server without a sleep is probably not a realistic scenario, at least for this application. I ran this test with 10 users from my local machine, but I also outputted the results to K6 Cloud. So this is an optional step, but I just like the extra visualizations. Remember that I like out of the box. I don't like to have to set this up for myself. So there is a shareable link to this dashboard in the slides. So later on, if you want to, you'll be able to have a look at it, what it looks like on K6 Cloud. And there's a bunch more that you can dig into. And then I looked at the Prometheus metrics of my application on Grafana during the test. And this is what it looked like. This is the network IO. This is a CPU utilization across all 3 nodes. It's an average of the 3. And then this is the memory utilization, but it's already broken up into the three nodes. So this is what I learned from this baseline test. From the side of the K6 test, I had 10 users running for a total of 1 hour, of which 45 minutes was a constant load. And the application had a 95th percentile response time. So I was looking specifically for requests that returned an HTTP 200 because if you include the response time for errors, it's going to skew your response time, because they might have, sometimes errors are either faster or slower, which can present an inaccurate response time or an inaccurate interpretation of what actually happened. There's also 1.16 error rate, which is honestly to be expected because I was getting Pokémons from a CSV file. I didn't want to just be requesting Pikachu every time, but there was a CSV that had not been put into the database yet. Now, the response time isn't great, so 4.223 seconds response time, meaning that 95% of all the requests had a response time of 4.2 seconds or less. But this is a demo application, so I don't actually expect it to be production ready. So from the server side, the CPU utilization was a maximum of 53% across all 3 nodes. The memory utilization was 60% at its highest point. None of the nodes had a CPU or memory utilization that exceeded 80%, which is like a good rule of thumb that I like to look for. There were also no pod restarts, and there were 32 running pods at any given point during the test. So these are all solid, specific, quantitative ways to measure the normal behavior of the application. I'm doing this on purpose because that way, when one of these metrics strays too far from what we now know is normal, we'll be able to identify it. And this is why it's not enough to just say fast enough, because we need to think about what that actually means. So the second step is to formulate the hypothesis. What experiments do we want to run? And how do we think the application will respond? Well, I knew I definitely wanted to do some sort of load test. Given that this is a demo app, I think that a 40 user test is already 4 times our baseline, so that's enough load. I also wanted to know what would happen if one of the pods was terminated. So how long would it actually take for another to take its place? It's not really important to think about why that pod might be terminated. Remember that we're doing chaos testing, so we are asking what if, not why. What if it happens anyway, for whatever reason? So to figure this out, I wanted to be able to make the second experiment involve terminating an app pod. And the third one could be to terminate a web pod. To complete these hypotheses, I identified 2 of the metrics. And in each of these experiments, the average error rate should still be less than or equal to 5%. And the 95th percentile response time should be less than or equal to 5 seconds. So there's actually different combinations of that. So only 3 experiments, but 6 different hypotheses. Step 3 is running the chaos experiments. This step is where hypotheses are proven to be true or false. It's not a failure, and that's one difference between chaos experiments and testing, right? Because in testing, a test passes or fails, and a failure might give a negative connotation. But it doesn't actually, sometimes it's a good thing, right? When a test fails, because then you have something to go on. You have something that you can improve. For the first experiment, I modified the same K6 script by ramping it up to 40 users, and then I left everything else the same. This is what it looks like on K6 Cloud, this chart here. The 95th percentile response time was significantly higher than that of the baseline at 17.66 seconds. Surprisingly, the error rate didn't really increase significantly, ending at an average of 1.22%. So that hypothesis was true. This one was false. The next experiments included terminating Kubernetes clusters. Now, really, I could have just rerun this test that I ran on using K6, and then I could have run some kubectl commands on my terminal while it's running to, target specific pods and terminate them. And that's totally valid. But the thing is, what if I have to give it to a colleague to run? Then I would have to have instructions for how I do it, exactly when the termination happens, meaning it's not really repeatable. So the approach that I took was to include it right in the script. So cool thing about K6 is that it can be extended. There's a tool called XK6, which allows you to add extra functionality to K6. So you have K6, you have an extension for it, and then you put them together using XK6. It's still just building your own K6 version. So for chaos testing, I used an extension called XK6 Chaos, which was made by a colleague of mine at K6, Simon Aronson. These commands show how to install XK6, then how to create a custom version of K6 that includes XK6 Chaos, which is the chaos engineering extension, and then finally how to run a test using that new extended version of K6. But first I had to add chaos testing to the script. This is just creating the version of K6 that will allow you to add chaos to your scripts. This is what I had to do. This is what I had to add to the K6 test that I showed earlier. Whoops, here we go. In this screenshot, I'm showing only the chaos testing part. It consists of one function, which is kill app pod. It retrieves the list of pods using pod list, and then it iterates through each of the pods that are returned, looking specifically for one whose name starts with app. And I could have specified an app here, like the full name of the app, but because I treat my pods like cattle, not pets, I'm not attached to specific pods. I wanted to be able to target any pod that's named app. And then it terminates that selected pod. So this is a slightly different approach to chaos engineering than what exists in other tools. Because usually chaos engineering tools are declarative, which means that you have to write your chaos experiments in YAML files. That means that they're also limited because you can't easily include conditions. So this is really what chaos testing should be like, I think. When it's in JavaScript, you could terminate random pods, you could terminate multiple pods, you can terminate only app and web pods. You can add a whole bunch of conditions that are not available to you when you just have a YAML file. You could even skip termination of pods depending on maybe the results of the load test or the last response time for a particular component. That's not available if you just have a YAML file. Here's how I put it all together in one script. This is the options section. So I showed this one to you earlier. The catch-em-all is the one where I get the Pokemon, I query the application for the Pokemon, and then the kill app pod is what I just showed you, which is the chaos engineering part. And this is just like the scheduling, basically. So I have two scenarios here. The first is this load testing part, which is currently set to have a 15-minute ramp up to 10 users, and then it'll remain constant for 45 minutes. And then the second scenario is the chaos test, which will execute the kill app pod function. It'll run only one user, since we only have, in this case at least, I only wanted it to happen once. And I also put a start time of 30 minutes. And that way, the users will already be ramped up. There will have been time for to get data during steady state. We'll have time from before. We'll have data from before the test as well as after the test, so we can kind of compare, because they should be the same. And if they're not, then that's useful information too. And then I also set up thresholds. Thresholds are ways to set conditions for your test. And if the test doesn't conform to those conditions, then K6 will fail the test. And it can also actually stop it if you want to. So the first threshold says that the error rate, the rate of failed requests, should be less than or equal to 5%. And the second one is that the 95th percentile response time should be less than or equal to 5,000 milliseconds or 5 seconds. So those mirror my hypotheses, right? Now for the results. This is the experiment where I terminated the app pod 30 minutes after the start of the test, at the point indicated in the screenshot here in the middle. So I expected the error rate to be noticeably higher, at least until the pod was replaced. But the interesting thing is it's not even really visible from here. If I didn't point out this point 30 minutes in, it probably wouldn't even be that noticeable. The response time was slightly higher, though, at 5.311 seconds, and that's just outside of the hypothesis. So the response time hypothesis would have been false, but the error rate hypothesis would have been true. So I want to also show you this, since we have some time. I hope this is big enough. This is the script. It's what I showed to you earlier, but I also wanted you to see it running. So these are the pods that I've got up right now. And let's just see, there are 3 pods in app. I'm praying a bit to the demo gods here, because, sometimes these things don't work out. But there's a C, V, and X. Now I want to show you what it looks like when it's actually running. But so I dramatically reduced the duration, just because, we need to be able to see it right away since this is live. But I'm going to run this entire script. And hopefully we should be able to see one of those app pods get terminated. So you can see here, this is the chaos scenario. Oops, that just ran, see? And it terminated one of those, the app pods, the C pods. So this is where it goes through the loop. It chooses the right app, and then it kills that app pod. And now we see that there are currently 35 pods. Let's stop this. So there's a bunch of information. I kind of stopped the load test right in the middle. So don't mind the errors there, but I'm going to, actually, I already did it earlier. So there it is, that C pod that was there, the app that started with a C at least, is now gone, and the age of the new one is 34 seconds. So that's the chaos engineering script at work, right? Because it just terminated randomly one of the app pods. I just wanted to show you that before I went forward with the rest of the experiments. So this experiment involved the termination of the web pod. It's kind of the same thing that I did with the app pod. It's just that I changed the app part into web. You could include a different function if maybe you want the app pod to be terminated at a certain time, like 30 minutes in, and then the web to be terminated 45 minutes in. That's the advantage of this approach. Anyway, the average error rate was 1.09%. So again, these points indicate when the termination of the web pod happened. And the average error rate was pretty good, 1.09%, but the response time was 5.09 seconds, only slightly, very slightly higher than what I expected. And this is the 95th percentile, I should be clear. Thanks for the comments about the presentation. It took a lot of practice. Now, if we just stopped here, what we've looked at so far is just the K6 side of the story. But K6 is outside of the box, so it's valuable information, but my point is that we're not looking inside the box, which is a lot of information that we're missing out on. Here are 3 experiments that I ran, the 3 that I talked about, just as a summary, with a total CPU utilization for each of them during the test. So if we go over the results of our experiments, the error rate hypothesis passed for all 3 of them, meaning that the average error rate stayed below 5% for all 3 experiments. But the response time hypothesis failed for all of them as well, meaning that the 95th percentile response time for the transaction that I was measuring, at least, was higher than 5 seconds. Now, it could be that the response time that I chose was a little idealistic, and maybe that's part of it. And indeed, the app and web pod terminations didn't significantly exceed the hypothesis. That's 5.3 and 5.09. That's not too far off. But the fact remains that the chances that a hypothetical user using the Poke API app in each of these 3 scenarios would be more likely to leave because of the response time and not because of the errors that they got in response to their queries. So the question is, why was the response time so high? So the first thing that I looked at was the CPU utilization, which is why I have these graphs here for each of the tests. The problem is that these are averaged out. Remember, I said that they are this is the utilization of the entire cluster, so all 3 nodes. And whenever you average out or aggregate, you're missing some data. What did I miss this time? So because I had the server-side metrics, I started to explore them to see what I could find. And I also drilled down into the CPU utilization of the individual nodes. And I found this sort of weird behavior where the CPU flatlines against 80%, but doesn't cross it. It's a little unnatural. I didn't see it when I was looking at the total CPU utilization. And then I remembered something. See, the last time that I gave this presentation, one of the suggestions that I received from others who are more experienced in Kubernetes than I am is that I should create resource limits. So that's totally sound advice, right? If you can scale out your cluster to make sure you still have enough resources for your app. And I, on my fledgling little cluster that I was paying for personally, didn't have enough resources for the app. So it turns out that Kubernetes treats CPU like a compressible resource, which means that as it approaches that limit, it's going to throttle that container. So there's this weird thing that happens where it actually might end up worsening the application performance if you add resource limits, if you haven't set it up correctly. To test this, I reran the experiments, but this time I removed the resource limits entirely. The biggest difference was here in experiment A because it was the one that was already kind of against that limit in the first place. So the one above is for a test where I didn't have those resource limits set, and the graph below is for a test where I didn't have resource limits at all. Without the resource limits, this 40-user load test did indeed blow past the 80% line and go up as high as 100% at some points. But what about the response time? This is really interesting because without the resource limits, the 95th percentile response time was 13.31 seconds. Okay, it's not like this isn't enough of an improvement for the hypothesis to be proven true, but it's still 24.6% lower than with the resource limits. The story continued with a second experiment. I didn't think it would make much of a difference, since the CPU utilization with the resource limits wasn't very high at 10 users, but I was surprised because without the resource limits, the CPU utilization of one of the nodes did increase above 80%, and the 95th percentile response time improved to 4.77 seconds, well within the hypothesized figure of 5 seconds. And here's what the third experiment looked like when I removed the resource limits. This is the web pod termination. This one had already been pretty close to the response time hypothesis. So when it was able to use just a little bit more CPU, you can see it going above, at least for one node. The response time did drop significantly to 3.63 seconds. So just a quick note here that the problem here was not resource limits, okay? The problem is that the app is CPU intensive and wasn't getting enough processing power to respond to those requests in a timely manner. Ideally, I would institute resource limits, but then also scale out my cluster. The main takeaway is that I should be able to look at it. The takeaway is that being able to look at the data has allowed me to spot issues with my configuration, even though I didn't expect it. I didn't go into this questioning what I'd done in the resource limits at all. Honestly, I didn't think it would make a difference in a negative way. So, the main difference between traditional monitoring and observability is that in traditional monitoring, you're looking for specific metrics, and then you set up counters to measure those metrics. In observability, you measure everything that's in the box in a non-obtrusive way so that you can explore that data later. In this case, I wasn't testing my container resource limits, although looking back now, it seems pretty obvious that I should have been. Instead, it was only by exploring the data and looking into, by chance, individual node CPU utilization that I got the clue about what was happening. So I didn't know in advance what I was looking for, and that's the benefit of observability. So let's go back to our Pokémon in a box. When we're testing an application for its reliability, being able to see into this box is essential because without it, we can launch test after test against the application, but we're not going to get any feedback in return. Even when the load testing tool is giving us information about the test itself, it's not enough because it's only telling us what we're doing, not how the Pokemon is doing. And that holds true for chaos experiments as well. This means that we can't really draw any meaningful insights about how the Pokemon will behave when exposed to the real world. Observability tools like Prometheus and Grafana make the box transparent so that we can actually see what's happening. Setting up the right monitors lets us get acquainted with how the application behaves when it's not under stress, which also lets us identify immediately when, and maybe perhaps set notifications for it as well when it's struggling. Observability gives us a better understanding of the events that our application cannot handle, and then also the events that it can just take in its stride. It's only through observability that we can really determine whether the Pokemon is alive or dead. Thank you for watching and listening. Thanks for your attention. I will take any questions if anyone has any. And as promised, here are my slides. You can go to them and you'll find all the speaker notes as well.
Thank you so much for this presentation, Nicole. I think you've already read some chats from the people listening to you, and they loved the art style, how you're doing it with changing different screens and etc. So congrats on that.
Thanks. I'm so tickled that people actually noticed.
Yes, I'm now looking at the Q&A section, and Dennis has a question for you. He's saying that, do I understand it right, that practical implementation of chaotic testing is all about switching off cluster nodes? What if an app is running on one server? How can chaotic testing be applied?
Okay, well, firstly, just because an app is running on one server doesn't mean you can't have multiple pods. So I did happen to have three servers, three nodes, but I started with one. So you can still, if you're on a Kubernetes cluster, then you can still do that. And then also, um, being able to terminate pods is one thing that you could do, but it's definitely not the only thing. So there are a bunch of chaos engineering tools that you can use, open source and proprietary. Probably one of the best proprietary ones is Gremlin, and they have like app termination, network latency, black hole. Like they have so many different experiments. The problem with that, and it's not just them, right? There's also like Litmus Chaos is open source. There's Chaos Monkey. There's Chaos Toolkit, but the problem is that they don't really integrate well with a load testing script, because I'm not a site reliability engineer. I'm a performance tester. I like scripts. I don't really like YAML files, to be honest. And I like being able to say, if this, then do the termination. Otherwise, maybe do this other thing or terminate more or something like that. So again, so to wrap up your question, no, it's not the only practical implementation, but it is the one right now that I've seen can be used within a load testing script. I mean, isn't it so cool to have both in just one script? I haven't really seen that approach anywhere else. Hope I
Okay,
answered
thank
your
you.
question.
I hope so too. I actually have somewhat of a follow-up question.
Okay.
Yeah, everything that I've been reading about chaos testing is uh, seems like geared towards very big companies with huge, complex infrastructure and architecture and everything else. What did you notice? When does it make sense for a company and a product to start looking into this and start using this?
Oh, sorry. David is saying he'd like to see the last slide again, but I will just type out my site where you can see the entire slide deck. Yeah. So when does it make sense? I think when you have a person who can do it, because yeah, that is the expectation. And by the way, that's the expectation testing too. Plenty of people don't do load testing at all because they think you need a complex architecture or you need someone with super fabulous skills or something. This application is not a production ready one. It's one that I made myself. I'm not a developer or a site reliability engineer, so it's not like super optimized, but I still do it because it's just a script. It's just a function in a script. And I think we need to scale back and think, okay, chaos experimentation doesn't necessarily involve incredibly destructive behavior. Part of the principles of chaos engineering is that you start small. So you start with like a very tiny thing that probably won't make a difference. You'll notice that my baseline was 10 users. I didn't say 1,000 users, let's hit it and break it. I actually did 20 first, then 30, then 40. Now let's terminate one pod. Like I could go work my way up to terminating all the pods, right? But you just have to find that risk level. You have to be comfortable with it, especially if it's in production, and do things like maybe don't run these experiments at a peak load time. Run it at like Sunday at 2 a.m. or something, as an example.
Yeah. Okay. Well, thank you for the answer. I think it clears some things up. And now we have just 1 minute left for this presentation. So if anybody has any more questions, please type them into the Q&A. And I have from myself a last question. I see that the background behind you is sort of a set for a podcast. Do you do? Do you do podcasts, and do you want to plug them?
Not really a podcast, but I do a live stream. I'm part of K6, so if you search for K6 test and on YouTube, I do a weekly live stream called K6 Office Hours, where we just talk about cool things people are doing on K6. And no, it's not a virtual background. It's real, and it just cost like 30 euro or something.
Okay, so thank you. People will definitely they will come and look for your streams. I don't see any more questions being typed, and we have like 10 seconds left. So thank you, Nicole, very much for your presentation. Thank you, everybody from the audience, for coming, and see you all a bit later in the next talk. And now it's lunchtime.
Thank you, everybody. Have a good rest of your conference. Now we have 10 seconds.
Yes.
Stopping stream in 3 seconds. Bye.